All right, let's get started. So I've handed back homework 7. You all have the solution, so I'm not going to go through that. I gave you that before the exam. Okay, now let's see. Homework 8. It is due on Monday. Does anybody have any questions on it? It is a pretty short assignment, so probably spend more time looking up values than actually writing them down, because it's all about looking up your adjustment factors and all that.
No, we had steel homework due today and a concrete test on Wednesday.
I really don't know how to expect you to start.
Now, all I gotta say, now if I go back, that calendar, it's been on them slides. Just saying.
Yeah, we knew it was coming.
Yeah, we knew it was coming, but we had bigger fish to fry.
We still have the last split fish today.
All right. Yes, I am. I skipped too far ahead. Okay, so again, this is I think the trade-off for having this due on Monday is that, it really is a pretty short assignment. And the development length examples, I think if you remember, once you looked at all your values, they were pretty short. Not a whole lot of math that needs to be done. There's just one formula. So it's not that bad. Today, what we're going to do is we're going to talk about columns. It's our big final topic of the semester is columns. We're going to discuss basics on capacity. There's a lot of rebar limits and sort of nitpicky details that you just need to make sure that you're following. But all in all, columns are pretty simple too. Just for lack of a better way of saying it, it's just 0.85 FC prime times the area of your concrete and Fy times the area of your steel. It's pretty much it. But we'll take it one step at a time. Okay. Now, if you notice on this slide, I've got, and on this slide, there are really two different types of columns that we're going to address in this class. One of them is going to be columns where all we have is axial load. Here's a column, here's a force, pushing on it. That's about it. We are also going to consider columns subjected to not only axial load, but bending moment as well. These are columns that would be fairly typical inside let's say, a moment frame in a building. And you've got gravity load from the building, the subweight of the building and the live load and snow and all that. And then you've got, let's say, wind or earthquakes pushing laterally. So those column elements are being subjected to axial load and bending. We tend to refer to those elements as beam columns because they're subjected to bending and axial load. They take a little bit more discussion, but all in all, I think you'll find they're also pretty straightforward. A beam column. We can call them column beams. What's that?
I like beam column better.
You like beam? I like beam column better. Thank you.
That's what I feel like they just got lazy. They feel like that's something else. We're going to call them beam.
You come up with another name. And
Maybe they didn't call them beam, but they would call them beam.
Good enough.
using that West Virginia accent to put it to good use. Okay, all right. Let's start off. We're going to start off by handling elements that are under pure compression. We'll also maybe later talk about buckling if we have time. The way that we handle buckling in here is far more simplistic than the way we handle it in steel design. In steel design, we have a very refined column curve. In here, we just basically use Euler buckling, so it's pretty straightforward. We're going to start off by handling pure compression, and if we eliminate the effects of buckling, then basically the concrete in the columns is limited to 0.85 FC prime. I'm calling them short columns because short columns, that terminology basically means we're eliminating the effects of buckling. Short columns, when designed, would tend to be designed more stocky than columns that would be subjected to buckling. So, you know, it's a conservative approach to neglect it anyways. Now, when we're talking about reinforced concrete columns, there are two types of columns that we're going to address. In some ways, they're handled similarly, and in some ways, they're not handled similarly. But we have square columns and we have circular columns. Now, square columns tend to be reinforced not only with longitudinal bars going up and down resisting the axial load, but we also typically have a series of longitudinal ties, sort of tying the rebar together. For circular columns, it's more common to use spiral reinforcement instead of longitudinal ties to see that spiraling reinforcement going down like that. Handling the spiral reinforcement versus the tie reinforcement incurs a few details and a few different checks that you have to perform. So you just need to make sure you're dotting all your I's and crossing all your T's. The actual proportioning and the design of the columns is pretty simple. Now, all right, let's talk about each of these. So if we're talking about square columns and tied columns, first off, the ties, what do? Well, first off, they hold the longitudinal bars in place during construction. So if you've got a bunch of longitudinal bars getting ready to have concrete cast over them, the bar or the ties just keep the bars in place, so they serve that purpose. They also serve to prevent the bars from buckling after the concrete begins to fail. Yes, sir.
So the columns subjected to purely axial load. It's like axial load in compression, so columns in compression. Concrete behaves very well in compression. Then why do we put steel in it?
What? You talking about?
The reason we put steel in concrete is because concrete doesn't behave well in tension, but when if you put this thing in compression, then why would you put steel in it?
That's a fair point, and I think you'll see the answer here in a little bit. I think you'll see the answer here in a little bit. Just bear with me. Bear with me a little bit. All right. Tell you what, I'll skip ahead and show you. Here's why. Okay? Because as you load the column, what's going to happen is the first thing that's going to fail is this outer layer of concrete. Okay? This series of tie reinforcements is going to serve to confine what we're calling the core of the column, and it's going to give you a little bit of a warning after failure. So that's really well, kind of, yeah. Yeah, kind of. What?
Oh, you say a warning after failure just kind of sounds like.
Well, before it really goes.
You broke already. So game over.
Well, what I'm getting at is that your outer layer is going to fail first, and if you see that, then it's time to go before the whole thing comes crumbling down. Without that rebar confining the core, you wouldn't have anything confining the core, and the whole thing would collapse. That make sense? Now, I will say one thing to keep, let me show you this, just to answer a further question. It's not as if we're loading the column full of rebar. We're not putting really a lot of rebar in it. When we design columns, we're keeping our reinforcement ratio anywhere from 1% to 8%. So a really heavily reinforced column would have 8% of its area comprised of rebar. Most cases we're looking at like 2% or 3% or something like that. So if our whole column having only 2% of it be rebar, that's pretty good. So it's not like we're dumping piles and piles of rebar into it. Make sense? Okay. Now what was I talking about? Goodness. Square ties. Okay, all right. So wow. End of the semester's happening, isn't it? Is that what it is? All right. Okay. Now, okay. one of the things about columns, and I know that I'm going to mention this, and I know that a lot of people around here are going to hear this, and it's going to go in one ear and out the other, is earthquake applications. You know, around here, we don't really need to worry about it, but depending upon where you all get a job or depending upon where you're working, I mean, it might be something you need to consider. That tie reinforcement, as you're mentioning, one of the things that it can serve to do is confine the core of the column, which will give you, without getting too into the details, having better core confinement will give you better performance during earthquake applications. I mean, you got to keep in mind when a building is subjected to an earthquake, it's being rocked back and forth with fairly large loads. So having a fair amount of confinement in that column definitely matters. Okay, does that make sense? Okay, and you get different performance whether you're dealing with a square column or dealing with a circular column. I'll say this, circular columns, and particularly that spiral reinforcement, it actually is a little more effective than square columns. It's also a little more expensive. So it's just about, you know, what the applications are and what you can deal with on a given project. If you were dealing with something out west or something in a high seismic zone, I would probably recommend circular columns just because that spiral reinforcement is going to confine the core a little better. But again, I think it depends on your given project. Does that make sense? Everybody good? Okay. Now, to compute the capacity of a column, it's pretty simple. Okay. So to start off, we're going to compute its theoretical capacity. Okay. Now, what's its theoretical capacity? Well, it's just 0.85 times the 0.85 FC prime times the area of the concrete, and it's Fy times the area of the steel. Okay, so 0.85 FC prime times the area of the concrete. What is the area of the concrete? Well, it's the gross area of the column minus whatever steel is in there, right? Make sense? Okay, plus Fy times the area of the steel. Make sense? Okay. Now, what we're then going to do is we're going to take that theoretical capacity and we're going to adjust it to, yes? Not really. It's just the notation that ACI goes with. Not really. Yeah, because we're talking about, you know, like samurai sword or lightsaber or cake cutter through the section, and we're just talking about that longitudinal reinforcement. All right? Make sense? Okay. Now, we're going to adjust this a little bit for what we're calling accidental eccentricity. You know, one of the things about assuming purely axial compression is that you're assuming that the load is acting purely dead center, square in the middle of the column. Okay? That might not be the case. Depending upon your construction, depending upon wind effects or something like that, that load might shift over to the side a little bit. So your capacity might be reduced a little bit to account for the fact that that load is a little bit eccentric. Okay? So we reduce that capacity a little bit with this term alpha. Okay? So this term alpha is not a safety factor. Okay? I can see it right now. Why do we adjust our terms on alpha on question 3 on the third exam? Well, that's a factor of safety. Nope, not a factor of safety. Okay? The factor of safety is the phi value. Okay? Now, a couple things. Phi is incredibly lower for columns than it is for beams. Okay? Going to what Mr. Schaefer said, he said, well, if concrete's very strong, performs very well in compression, you know, that's a good thing, right? So why is our phi value so low? Here's the reason why our phi value is so low. I don't know if explode is the right word, but actually, you're actually not that far off. When concrete, look, if I take an element of concrete and I subject it to compression and then subject it to the same amount of tension, if I compare its performance, concrete and compression can exhibit far more strength and, bless you, concrete can exhibit far more strength in compression than it does in tension. But what were you about to say? When you take a cylinder and you put it under compression, it goes and it goes quick. Okay? All right?
Yeah, that also legitimately disintegrates.
okay? I, please, please, no, no. Please, please. I've answered that question, and we're going to move on. But going back to what I was saying, I did answer it, and we're moving on. Going back to what I was saying, when you have an element in compression and it does fail, it fails quick, right? So, in other words, I don't think it's that far off to expect that we, have a factor of safety that represents that accordingly. We were using 0.9 for beams. For columns, we're using 0.65 if it's a square column, 0.75 if it's a circular column. Now, why the difference? Well, I say square and circular, but I guess what I should really be saying is tied and spiral. Again, spiral reinforcement tends to confine the core of your concrete column a little better. Imagine that cylinder if there was a little bit of rebar in it. See what I mean? You still have a drastic failure, but it wouldn't be as bad. Yes.
Won't you spiral it on the square ones too? You have the angles and stuff.
You can, but it tends to be a little more difficult. Plus, if you're going out of your way to need spiral reinforcement, then you're really more worried about column efficiency anyways. And if you're that worried about column efficiency, I would say a circular column is the way to go anyways. Circular columns tend to be more efficient than square columns anyways. The reason that we use square columns is because they give us a square edge and they're easier to construct. But circular columns are more efficient. So it's really more about what it is you're after. If you're in some high seismic zone where you really need to worry about structural efficiency and confinement, then I would just go with a circular spiral column. It's going to be more efficient anyways. But if you're around here and you don't need to worry about earthquakes, I would just keep it simple and go with square and go with tied. I'm not saying there's any reason you couldn't mix it up. I just don't really see the economic advantage of doing that. Does that make sense?
On that spiral, since, like I said earlier, lightsaber, at that point, you got to take that?
No. We conservatively neglect that. However, the way that we handle spiral reinforcement is a little different. We'll get into that. Actually, the way that we handle the spiral reinforcement is actually going back to another Engineering 216 analogy. It goes back to pressure vessels. I know that my folks, when we did 216, we did pressure vessels in there. Do y'all remember thin-walled pressure vessels? Did you all do thin-walled pressure vessels? So, yeah.
That was the best part.
Oh my God. That's a reaction. Okay. So, are there any other questions related to this? Okay. All right. Note that for tied columns, again, our phi value goes up. Also, for tied columns versus spiral columns, for spiral columns, our phi value goes up. Also, our alpha value goes up as well. Again, spiral columns tend to confine the column better, so you get a little bit of an advantage from a capacity standpoint. Now, there are a number of detail-related requirements that I'm going to go into. And again, the reason why is because of what you said about the cylinder in the testing machine. What happens when concrete fails in compression? It goes quick, okay? So a lot of these column reinforcement requirements may seem a little detailed. There's a reason why, okay? So first off, percentage of longitudinal steel, you're going to have to provide some, but you don't want to provide too much because, of course, you all know by now you have to have enough concrete to develop that reinforcement. So the rule that ACI dictates is that your reinforcement in your column has to be somewhere between 1% and 8%. So your rho value is just the area of the column divided by, or the area of the steel divided by the area of the column, and that's got to be somewhere between 1% and 8%. Now, if you're using ties, you got to have at least 4 longitudinal bars, and if you're using spirals, you got to have at least 6 longitudinal bars. In terms of design, a practical minimum column dimension is about somewhere between 8 to 10 inches. Like I would never construct a reinforced concrete column that was just 6 inches by 6 inches. I wouldn't do that. Practical minimum dimension somewhere 8 to 10. 12s also are pretty common. Okay? There's some additional requirements for tied columns. Okay? Now, the minimum size for a tie. Okay? Now, let's take each of these one. Okay, the minimum size of a tie is either number 3 bars or number 4 bars, depending upon how big the longitudinal bars are. And the idea behind that is this. Imagine if you've got a column, right, that's got number 18 bars, these really, really massive bars, and you're tying them together with number 3s. Pretty flimsy, right? You got to have something with enough beefiness to it to actually tie those bars together. So if your longitudinal bars are number 10s or smaller, use number 3s for the ties. Otherwise, you use number 4s for the ties. Now, your minimum tie spacing is either 1 inch or 1 bar diameter. Now, that would be a lot of ties. Okay? Usually, we're trying to go off of the maximum tie spacing, which is the minimum of either 48 tie bar diameters, 16 of the longitudinal bar diameters, or the least lateral column dimension, which more often than not with columns, we're doing our best to keep them square. I mean, you can't have rectangular columns, but we do our best to keep them square. Does this make sense? I know there's a lot of details on here, but that's sort of the name of the game when it comes to columns. Everybody okay with this?
Is it just for square?
Yeah, for tied columns, yes.
Dimension for a column? Is there any maximums?
Not really, but I'd argue that's not really a big deal. I mean, if you're design, are you talking about a column in a building? Like, I'll say this, without getting too far into the concrete world, you really don't encounter maximum column size problems in buildings. You can in bridges, okay, but not for the reasons that you would think. There's actually a fair amount of research that goes on in the world of what's called mass concrete, and it's specifically related to temperature issues. I mean, you all know enough about concrete to know that you have to have a certain temperature in order for the concrete to cure properly, right? Well, if you've a block of concrete that's 20 feet by 20 feet, are you telling me that the concrete in the center has the same material properties as the concrete out at the end? No, that's okay. You might have issues with loss of hydration or containing too much hydration, or et cetera. That's not really going to be a problem in a 12-inch by 12-inch column, but on a massive, massive bridge pier, it might be. That's a whole nother can of worms, so a whole nother issue. For most building applications, that's never a problem. I mean, if your column is getting that big, then the obvious answer would be just throw another column in there. See what I mean? So that's a good question, and there are limits, but for a completely different application, completely different reason. Sound good? All right. Okay, additional requirements for cast-in-place tied columns. No longitudinal bar can be located more than 6 inches from another bar. That's just to ensure that your ties are, in fact, being effective and keeping everything together. You can use 4 bars and keep them, in the corners. That's fine. But if you throw another bar in here, you got to make sure that that's 6 inches. You don't want your ties to be ineffective. Let's see what else. Okay, so cast in place for spiral columns. This is a little bit of an odd requirement to mention, but I guess I should, that your spirals can't have a diameter less than 3/8, so they got to be number 3 bars or larger. In the code, so I thought I'd mention it. I think it's a little bit of an odd spec, but should be worth mentioning. Now for spirals, your clear spacing has to be between 1 and 3 inches. So a very, very common spiral spacing is 2 inches. Okay? So that's just something to keep in mind. Again, you're wanting your spiral to confine the core of your columns. You actually do kind of need a lot of reinforcement. Yes?
Back a slide, what's this little symbol that's like on the corner of the column?
What's
Around
that?
the bar there?
Oh, that's a good question. Let me sort of draw it out. So that's sort of like if you're tying or if you're bending the tie, you're going to have that, 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 and then that. So that's all that is. It's just the rebar being bent out.
I think we would all prefer that that's called the clear tie.
Go right ahead. What's that? The tie bow. That's bringing it back. That's a reference. Okay. Does anybody have any questions about this? Okay. So what we're going to do is we're going to do an analysis problem of a square column. Then we're going to talk a little bit more about spiral columns and do a spiral problem. Spirals, they need a little bit more discussion. So really what I'm interested in is understanding what is the capacity of this column and making sure that you can do all of the appropriate checks. Okay? Sound good? Everybody okay with this? All right. So we have a column. It's 16 inches by 16 inches. I have 8 number 9 bars. The ties are number 3 ties, and they are spaced at 16 inches on center. Okay? I've got 1.5 inches of cover from the face of the concrete to the ties, and then the bars are inside those ties. Make sense? Everybody okay with that? So just so everybody's clear, what we've got is a column that looks like this. We've got that, we've got that, that, etc. And then we've got these ties going like that. And then these are 16 inches. Does that make sense? Everybody okay with that? Okay. All right. So example. All right. Example 18a, so column parameters. All right. Pretty straightforward stuff. Now the column size, what was it, 16 by 16? So we'll say B equals H equals 16 inches, which I guess that brings up an interesting question. Which is the B side and which is the H? I mean, is that B and that H, or is that B and that H? It doesn't really matter because it's just in compression. Now, what is the area of steel reinforcement? 8. There we go. Eight square inches. Okay. Now, the actual design capacity of the column is going to be a very quick calculation. Okay. It's all the checks that are going to take a long time. So design capacity. All right. What is phi going to be? And what is alpha going to be? For a tied column. Make sense? All right, so therefore, there's your capacity. Pretty straightforward. Our theoretical capacity on the inside, so 0.85 FC prime times the area of the concrete plus Fy times the area of the steel. Pretty straightforward, right? I mean, not very complicated. So 0.65, 0.8. What do we got? We've got 0.85. What's that? Well, now you know that we're talking about columns, though. If you see the AS, that's for beams. What's that? My goodness.
It's a different question. That is a question.
What was it? I didn't even hear the different question.
You melt steel columns. We know they can't melt steel beams.
All right. The gross area of the column is what? So wow. It's the semester. Is it semesteritis? Is that what it is? I thought it was semesteritis because.
Just wait till next semester. Nah, not hours to get out of here.
Oh. Folks watching the YouTube, they're missing out on all the jokes. 688.1 what? Now we're not done because we've got checks to make. So. All right. All right, settle down. Okay, we're going to take these one step at a time, okay? So let's start off with the steel percentage. So rho G is just our reinforcement ratio for the column. And it's just the area of steel divided by the gross area of the column, okay? Now, we have 8 square inches divided by 256 square inches. What does that come out to be? What's the deal with that? Good or no good? No. No. It's between 1% and 8%. That's between 1%. I said practical value is around 2% or 3%, but the limit is between 1 and 8. So, make sense? So, we'll say that's okay. All right. Next one is the number of bars. Okay. How many bars do we have in this column? 8. Is that okay? Now, this being a little esoteric, but you got to go through your notes. Why? What?
Because the spacing between the bars doesn't exceed 6.
Well, no, that's another limit we're going to check here in a second. What is the minimum number of bars for a tied column? Hold on. What slide are you on?
254.
254. At least 4 longitudinal bars must be used within ties, within rectangular ties. So, I ask you again, is this a good result? And here I'll put all right, minimum tie size. What is the actual tie size for this? The size of the ties. They're number 3s. Guys, come on. What? No, hold on. Say that again. No. It's not. Yeah, because the longitudinal bars are less than a number 10. Yes. All right. Okay. Now, let's check the minimum tie spacing and the maximum tie spacing. Now, what's the minimum tie spacing? Well, hold on. No. Minimum tie spacing is the largest of 1 inch or 1 longitudinal bar diameter. What are the size of these bars? The longitudinal bars. Oh,
Long way back.
it's in your slides. I believe it was slide number 62. 63. Was it slide 62 or 63? 63. Okay. Maximum tie spacing. All right? We've got 3 different limits to consider, right? 3 different limits. All right, what's the first one? 48 tie bar diameters, right? What are the tie bars? What are they? Number what? What's the diameter of a number 3? That's the area. What's the diameter? What? You said that really fast. 3/8. What'd you say? Okay. What is this? What's the next one? Guys, come on, settle down. 16 times what? There we go. What is this?
18.75.
And what's the least column dimension? Bless you. Bless you. It's 16, right? So the one that governs is the smallest, which is the 16. Is that okay, though? Yeah, that's okay, because our tie spacing is, in fact, 16 inches, right? All right. Sound good? Okay, now, if you understand that, then let's talk about the last one, which is the bar spacing. Do I need to stay on here? Has everybody got this? Everybody good? All right. All right, everybody. All right, settle down. All right, all right, all right. Y'all gonna want to pay attention on this one. All right. What is the limit on clear bar spacing?
6 inches.
Now here's how we're going to compute this. No. 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 You're close. You're on.
-3 divided by 2.
All right, all right. Hold on.
Let the man speak.
Hold on. Hold on, hold on. Now I'm drawing these at right angles, and they wouldn't be, but it makes the point, so it really doesn't matter. All right. Now how many bars are on a given face? 3. So I got 1. Actually, no, I can do better than that.
Sure, that was the number.
2. That's good enough. Okay, so watch how I'm going to do this. Okay, I'm going to say, we'll start off with 16 inches. Okay, now what I'm then going to do is I'm going to come in 1.5 inches on each side. I got cover on each side, so 2 times 1.5 inches. Everybody see why I'm doing that? So watch what I'm doing. I'm starting out, so follow with me. I'm starting out 16, 1.5, 1.5, right? Then what do? I come in, how much on each side? 2 tie bar diameters, which is 3/8. Now, what if I were to just do this calculation right here, that would give me this dimension right there, right? Make sense? Now what I'm going to do is I'm going to subtract 3 longitudinal bar diameters. Make sense? So watch this. Watch the screen. So what that's going to do is, imagine that green line. That's going to subtract that, and that. So what do I need to do to this calculation to get the clear spacing? There's your clear bar spacing. Does that make sense?
Would it be fair to say that the number on the bottom would actually be the number of bars minus 1?
That is correct. Because if you had 4 bars, you'd have 3 segments, so you'd have to divide by 3. Exactly right. If you had 6 bars, you divide by 5, etc.
That was exactly what I got 4.43.
My goodness, guys. All right, hold on. Let's restore order here. Is this good? There we go.
What are we comparing it to?
Well, you tell me what we're comparing it to. 6 inches.
What slide is that on?
Two slides ago.
256. There it is.
Okay. Does that make sense? Seriously? Okay, all right. Goodness. Class ends in a minute, so it's perfect timing, right? Why would you want to see that, Mr. Cruikshanks? Bless you. All right. Listen, all right. Let's make sure everybody's clear on the path coming forward. Okay, so you have a homework due on Monday. I have what? Well, I'll remember that.
We won't turn in the homework unless he turns in.
Let me explain something. Let me explain something.
All of us don't do it, we get 100.
You trust everybody in here? You trust everybody in here? I don't think you could coordinate everybody to do that. Hold on. You got me a cake, and then you would do this to me. All right. Let's make sure everybody's clear on the schedule. So you have a homework due on Monday. On Monday, I'm giving you your final assignment. It's not due till the following Friday. And it's not a very, very long assignment. It's actually a pretty reasonable assignment. I just wouldn't wait until the Thursday the night before, okay? Because especially for those of you that are in steel design, because you've got 2 homework assignments due. If you take your time with this, the steel and the concrete will go very smoothly. But if you do them both the night before, well, yeah. Okay. Everybody good? Okay. One other thing. In steel and in concrete, okay, and tell all your friends, on Monday, I'm bringing in the notebook, okay, because I've given out everything for the handouts. So it'll have, other than homework solutions, it's got everything. So if you're missing something on Monday, like, that's the day, okay? Sound good? I'll remember that one.
Gets under my skin. I took a chemistry exam one time, and the solution was stapled to the back. Somebody said something about it. I didn't know it was there. The TA stapled the solution to the back of everybody's exam. We're like 10 minutes in, and
All right, I'm stopping the recording on that one.